Hey everyone, I'm Mr. Morris, and I'm going to do an instructional video on accuracy versus precision. Now, accuracy and precision are not exactly the same. Now, you might think that they are because of the way that we use the word precise in everyday life, but there is an important difference, and you need to make sure that you know that. By the end of this video, the goal is for you to understand the difference between accuracy and precision. That's one of the objectives and the goals. Another one is to be able to look at a set of data and tell me whether it is accurate, precise, or any combination of accuracy and precision. The last thing that you need to be able to do is to use accuracy and precision when you're talking about lab equipment. We're going to talk about all of those things in this video. All right, let's get started. First of all, accuracy and precision are both talking about how close a measurement is to something. In this case, with accuracy, we're talking about how close a measured value is to the accepted value. Think of accuracy as being correct. Okay, if something is accurate, that means it's correct. It's close to the actual answer. So the accepted value for density says that here, and I could replace those words. I could say the actual density of gold instead of accepted value for. I could say the actual density of gold. It means the same thing. It gives me 19.31 grams per centimeter cubed. And then it tells me student A and student B both do experiments to figure out the density of gold. We get two different answers, 19.33 grams per centimeter cubed and 21.45 grams per centimeter cubed. We want to know which one is more accurate. Student A is more accurate, and the reason is because if you compare them, student A is closer to the accepted value than student B, okay? Because 19.33 grams per centimeter cubed is closer to the accepted value. Sorry, I wrote too big and kind of ran out of room, but it's closer to the accepted value. That's the idea. Precision is different, okay? We need to know the accepted value for accuracy, but for precision, we don't need that. But what we do need, we need a series of measurements, okay? Precision refers to how close a series of measurements are to each other. So accuracy means like correctness, how correct the answer is. Precision just means how consistent it is. So precision, another word for that, an everyday word for precision would be consistency. Okay, an example, distance measurements of 4.34 meters, 4.36 meters, and we have 4.33 meters. Those are more precise because they are close to each other. If they're close to each other, they're more precise. If they're not so close, they're less precise. Okay, so these distance measurements, 4.86 meters, 3.23 meters, and 4.02 meters, they're a little further apart, so they are less precise because they vary quite a bit. Or I might use this other word. It's a vocab word you probably ought to be familiar with. Imprecise. It's I-M and then the word precise. It means the opposite of precise because they vary quite a bit. Now, let's back up and do that again. Looking at these answers, they're pretty close. It's 4.3 something every time, right? This is 4.8 something. This is 3.2 something. That's a pretty big difference. So we can see that these numbers are closer to each other than these are to each other. That's why we say these are more precise. But what if it's not that obvious? If I just say, hey, which of these is more precise? And it's a bigger, it's a little harder to tell the difference, okay? If it's a tricky question, what you want to do is look at your set of data. Pick the biggest number. The biggest number in this set of data is 4.36. Then pick the smallest number, 4.33. find the difference. So subtract 4.36 minus 4.33. I'm going to get 0.03. Okay. Now I could do the difference between the biggest and smallest number here, 4.86 minus 3.23. So let's do that. 4.86 minus 3.23, and I get 1.63. Well, that's a bigger difference, right? If there's a bigger difference, it's less precise because they're not close to each other. But if it's a very small difference between the biggest and the smallest, that's extremely close together, it's more precise. So if that helps you to kind of figure out the tricky questions, you can use that tip. And if you come across a tricky question, you might want to just come back and find this spot in the video and rewatch it to explain how to do that, just in case you forget. Okay? Now, we can also use kind of a metaphor with this. Let's talk about a target analogy. If I were playing darts, I first want to ask, is it accurate? Accurate means that it's correct. So what's the thing I'm trying to hit? What's the accepted value? Well, it would be the bullseye, that part in the middle. Okay, so did I even get close to the bullseye on this? No, I did not. So I would say, no, this is not accurate. There's no accuracy here. Okay, did I get close to the bullseye there? No. No accuracy, or a low level of accuracy. Here, I'm getting a lot closer, so I could say, yes, that's definitely more accurate than the other two. And this one is exactly on the target. So I'm going to say, yes, that's accurate. Okay. Now let's talk about precision. Precision, remember, that's consistency. How consistent would you say this is? Not at all is what I'm thinking. So no, this is not precise. Is this precise? Is it consistent? Well, it's wrong. It's consistently terrible. It's about like me trying to throw darts or shoot hoops or something, okay? It's consistently terrible. So yes, it's precise, it's consistent, but it's not good, okay? Now this is getting better, but it's still not very precise because I hit in a different place every time. It's just that it was close to the target. But that's extremely precise and extremely accurate. So I'm going to say yes and yes on that. Okay. In my opinion, this is the trickiest scenario, and I rarely see those on quizzes or tests because it's a little bit more subjective. But you want to be really familiar with the others because you might see something like that in a test question. All right, let's go down a little bit more. The term precision also applies to laboratory measurements, so we want to make sure we're familiar with that. It's just another use of the word precise or precision. It's how accurately a measurement can be made. Smaller increments, or the graduations, the markings on your equipment, makes for more precision. So the more close together those lines are, the more precise it is. And the more far apart they are, the less precise it is. So if you look at these are pretty close together, but these lines are a whole lot more close together. So that's my most precise. It gets a 1. This is the second most precise. It gets a 2. And this is the third most precise. It gets a 3. All right, moving on to the next one. Okay. Now we're talking about how to correctly read laboratory measurements. I want to really stress this page. It's extremely important that you understand what we're talking about on this page. If you don't, you may want to rewatch the video, ask your teacher questions, get clarification, lots of practice, because if you don't do this correctly, it's going to come back over and over and over again, and it's going to make chemistry kind of challenging, okay? So make sure that you are good at what we're talking about on this page. All right. So it says scientific measurements are reported so that every digit is certain except the last one, and the last one is estimated. So that means when we're making a measurement, we're always going to estimate one decimal or one digit, not necessarily a decimal. Okay. In this case, the first 3 numbers are certain. Well, always the last number is estimated. okay? So when you're making a measurement, you need to make sure you're doing it that way, okay? I want you to know the word increment. What do we mean by that? We kind of just talked about it, but just to review, it's the measurement, it's the smallest measurement between two markings or lines. Now you could look at like something like this and kind of figure out what the increments are on it. Whatever those lines represent, that's the increment, okay? So in this case, each of these is going up by 50. My increment is 50, okay? That's the idea. So you've got increments on the things that you use at home, measuring cups and that type of thing, okay? Now let's look at a science example here. So now the pistachio has the same mass on both of these, but we're measuring it with a different amount of precision. Let's look at that, okay? So our increment here, what does each of these little bitty lines represent? Well, the ones that are numbered are representing tens place, right? I go from 0 to 10. But what about those little numbers in between? Well, I'm going to go with 1. I'm going to guess 1. And let's try it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's 10. So that's correct, okay? So the increment is 1. Because each time that I go past one of those lines, it represents the number 1, or going up to the number 2, 3, and so on. It's going up by 1 each time. Okay. My estimated reading, well, it's between 1 and 2, somewhere in between 1 and 2. So I'm going to say 1, but remember, we have to have an estimated number. So we're going to go 1 decimal farther, and we're going to estimate and guess what that is. My eyes aren't very good, so you might be able to look at your notes and just say, okay, well, that's 1.1 or 1.2, 1.3. I don't know. I'm going to guess 1.3. It's kind of hard for me to tell on that scale, okay? So let's kind of go through these bullets down here. If a measurement falls between two lines, the last digit has to be estimated. We're illustrating that up here. It's between two lines. You've got to estimate. Now, your answer might be 1.2 or 1.1 or 1.4 or maybe even 1.5. As long as it's reasonable, that's okay. Your answer might be different than mine, but you have to estimate. The answer 1 would be incorrect. The answer 1.20 would be incorrect. You have to estimate 1 place value, and that's it, okay? 1 extra place value. Now looking at this scale, I've got a more precise measurement because this is 1 and then 2, so that means that each of these lines has to represent a smaller number. 1.1, 1.2, 1.3, 1.4, 1.5, 0.6, 1.7, 1.8, 1.9, 2.0. Okay, so it looks like each of these must represent 0.1. And you can use trial and error to figure that out a little bit, okay? So looking at this, it's between 1.1, 1.2. It's between 1.2 and 1.3. So I'm going to say 1.2 something because it's between 0.2 and 0.3. Okay, 1.2 what? Well, I can't really tell, so I'm just going to guess 1.25 because it's very, very small. What if you said 1.24 because your eyes are better than mine? That's fine, but you have to estimate. Okay, that's the key. So let's talk about that down here. If a measurement falls between two lines, you have to estimate. If a measurement falls exactly on a line, then the last digit should be a 0. You're going to put an extra digit there, and it's a 0. Precise readings have to have 1 extra decimal place, more than the increment, okay? And then when we're reading graduated cylinders, this is a different skill. This little thing, this dip in a graduated cylinder, is called the meniscus. Okay? It's called the meniscus. Always read at the bottom of the meniscus. Okay? So I don't read up here at the top, I read down here at the bottom. Okay, we're going to compare these. Another thing in the lab, which we're not going to be in a lab for a little bit, but in a lab, you want to make sure when you're using a graduated cylinder that you hold it at eye level when you're reading the measurement. You don't want to hold it up because that's going to look different than what it actually is supposed to be. And you don't want to look down on it. That's going to mess up your measurement too. Read it at eye level. Okay? So let's compare these two. Look at our increments. I go from 14 to 15, and let's count those lines between it. So if I said, okay, 14, 15, 16, 17, oh, that's not going to make sense because that's 15. See what I mean? 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, that doesn't make any sense at all. All right, so it must not be 1. Maybe it's a smaller number. I'm going to go with 0.1 in this case, okay? So 14.1, 0.2, 14.3, 14.4, 14.5, 14.6, 14.7, 14.8, 14.9, 15. Okay, that makes sense. So we're going to go with 0.1 as the increment. And you'll get better at this and you won't have to do that every time. But it's important to make sure that you check it, okay? This goes up by tens, right? 10 goes to 20. That's a 10 jump. So let's try 1, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That makes sense. It fit, okay? So if it goes up by 1 milliliter. Our increment for this one is 0.1. Our increment for that one is 1, okay? So our estimated reading should have one more decimal place than whatever the increment is. So I should have not 1 decimal, but 2 decimal places in my answer. And I should have 1 decimal place in this answer because that's 1 decimal further than the ones place, the whole number, okay? I have 14.1234, 14.4. All right, it's tempting to leave it there because it's exactly on the line. But remember, you always have 1 extra decimal place. If it's exactly on the line, we're just going to put a 0 afterward. 14.40. Okay, that's our estimated decimal place. All right, and then this one, I'm going to go 10, 11, 12, 13, 14, between 14 and 15. So I'm estimating that at, let's say 14.4. Maybe you'd guess something different, but it's about 14.4. All right, I hope that makes sense. If you have any questions, reach out to me or to your chemistry teacher. Any of us would be happy to help. Thank you.